So today we are going to discuss about vector operators in curvilinear coordinate system. Before going to this, let us revisit some of the concepts of vector operators in Cartesian coordinate system. So we know that some of the vector operators so what are the vector operators? We have a grade operator, it's a gradient operator. Grade, we have divergence, we have curl, and we also have it is called Laplacian. Okay, so what is grade? Grade is nothing but it's a scalar operator which operates on a scalar function represented by phi. So grade phi is nothing but dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap, right? Similarly, divergence is a vector operator. It operates on a vector function. Let f be a vector function, then the divergence of f is given by dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, dotted with, let f1 be the x component of f vector, and the f2 is the y component, and the f3 is the z component. Then we have f vector can be represented as f1 of I cap plus f2 of j cap plus f3 of k cap, right? Similarly, for curl we have del cross f vector, okay, and it is given by the determinants I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z. Here we have f1, f2 and f3, right? Okay. So similarly, the Laplacian is given by del dot of grade phi, right? So it's a vector operator. It operates on the gradient of a scalar function. Okay, so it is nothing but dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap, dotted with gradient of phi. So it is dou phi by dou x I cap plus dou phi by dou y j cap plus dou phi by dou z k cap, right? So if we take the dot product, we have dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. Okay, so this is the Laplacian. This is a dot product. So these are the vector operators in Cartesian coordinate or rectangular coordinate. Usually it is represented by three mutually perpendicular vectors, and this is the representation for the Cartesian coordinate. So if we have a point in the Cartesian coordinate represented by a position vector r, then the position vector of p be r, right? So in Cartesian coordinate, this r is a function of x, y, and z, right? Because we represent r as x I cap plus y j cap plus z k cap, right? So we usually represent this r as x I cap plus y j cap plus z k cap. So if you want to find dr, then since r is a function of x, y, and z, by the basic definition of differentiation, we have dr equal to dou r vector by dou x into dx plus dou r by dou y into dy plus dou r vector by dou z into dz, right? So from, let this be equation 1 and this be equation 2. So from equation 1 we can write dou r vector by dou x equal to what is dou r by dou x? It's I cap, right? Similarly, dou r vector by dou y equal to j cap, and dou r by dou z equal to k cap, right? So in equation 2, the partial derivatives, this partial derivatives represents vectors, right? So these partial derivatives are nothing but are vectors. And in Cartesian coordinate, it happens to be a unit vector. Generally, they are vectors, right? So we borrow this idea and extend it to curvilinear coordinates, and there also we find these vectors, and from that we can derive the unit vectors for a different coordinate system. Okay, so these are the basic ideas. So let's move on to the curvilinear system. So these are generalized coordinates, and we can represent uh, them as follows. So let me draw a Cartesian coordinate system first. So this is our regular rectangular or coordinate or Cartesian coordinate, and this is our x, y, and z, right? So instead of this rectangular coordinate, we can also draw a more generalized coordinate which is something like this, right? So they don't need to be a straight line, so they can have a curve in the axis. So this axis or curved axis. Okay, so let's name this axis as u, v, and w. Okay, so suppose if we have a point P which has a position vector r in rectangular coordinate system. So this is our r vector, right? So this is our r vector. Similarly, we can represent this r vector. So what's the form of r in Cartesian coordinate? So in Cartesian coordinate, we know that r is a function of x, y, and z, right? So similarly, this r vector can be represented in the new coordinate system with axis u, v, and w. So this is our curvilinear coordinate. So the form of r in curvilinear coordinate can be given as r. Now r is a function of the new axis. Okay, so the r is a function of u, v, and w. Okay, so with this, let's try to derive the form for dr. Okay, so what is dr vector? So since this is in the u, v, so this r is in the new function which is a function of u, v, and w. Therefore we have dr equal to dou r vector by dou u into du plus dou r vector by dou v into dv plus dou r vector by dou w into dw, right? So we have already seen these vectors, right? This dou r by dou u and dou r by dou v and dou r by dou w are vectors. Okay, so in the Cartesian system they represent the unit vector, but here in this is the derivative of the position vector in what coordinate? In our curvilinear coordinate. Okay, so here also they must represent a unit vector. Okay, but not in a straightforward way. So in order to make this general vector to a unit vector, what's the way? So what's the way we can make to make the vector to a unit vector? So for that, to find the unit vector, what we have to do? We have to divide this vector, this dou r by dou u, by its modulus, right? Therefore, suppose if we have a unit vector like u, e of u, right? Then this unit vector is nothing but dou r vector by dou u divided by modulus of dou r vector by dou u, right? So in this way, it represents a unit vector. Similarly, we can form the unit vector for this v and w coordinates. So the unit vector for the v and w coordinates are, let it be represented as e of v, right? So e of v vector equal to dou r vector by dou v divided by modulus of dou r vector by dou v, and our e w cap equals to dou r vector by dou w divided by modulus of dou r by dou w. Okay, so instead of representing this in this way, let's rewrite this equation. So let's rewrite this E cap, EU cap, EV cap and EW cap as, so EU cap equal to 1 by HU of dou R vector by dou U, right? Where HU is nothing but modulus of dou R vector by dou U, right? So we are rewriting this unit vector to this form. Okay, similarly we can find EV vector, EV cap and EW cap. So they are 1 by HV into dou R vector by dou V and 1 by HW into dou R vector by dou W. Okay, similarly here also HV equals to modulus of dou R vector by dou V and HW equal to dou R vector by dou W. So what we did is we just rewrite this this unit vectors of the curvilinear coordinates into this new form. Okay, here this HU, HV and HWs are the scaling factor. So they are the scaling factors, right? So if we substitute this in our dr, what we have is dr vector equal to, we can write dr vector as HU EU cap du plus HV EV cap dv plus HW EW cap dw, right? So we rewritten this this derivative of the position vector of the curl in the curvilinear system as this. Okay, so it is somewhat similar to our, this is for the case of curvilinear, right? So this is curvilinear system. Okay, so this one is Cartesian. So it is similar to Cartesian system where we have, instead of this HU EU we have I cap, right? So I cap dx plus, let me rewrite this also in green color. So this dr vector equal to I cap dx, j cap dy and k cap dz. Okay, so we can see this is a unit vector, this is a unit vector, this is also unit vector and this is also unit vector. So these are unit vectors in curvilinear system, right? So they are general system. So this is also a unit vector. Okay, similar to I, J, K in Cartesian coordinate system, this EU, EV and EW are the unit vectors in curvilinear system. So before proceeding further, let's work out some simple examples so that we can get the idea of this curvilinear system, right? So let's use this curvilinear system to derive. So as I told already, they are generalized system. So they are generalized coordinate system. We can derive any form of coordinate system from curvilinear system. Okay, so let's use this curvilinear representation for the position vector to derive the derivative of the position vector in Cartesian system. Okay, so in Cartesian system, so we know that EU equals to, so in curvilinear system this EU vector equals to 1 by HU dou R vector by dou U, right? So in Cartesian system, this U, V and W are nothing but X, Y and Z, right? So if we substitute, so if we try to find this unit vector, we have, so our R vector is X I cap plus Y j cap plus Z k cap, right? Therefore, so EU, instead of U we have to substitute as EX. Okay, so this is the unit vector along the X direction. So EU equal to EX equal to 1 by hx into dou r vector by dou x, right? So we already know dou r vector by dou x equal to I cap, right? And our hx equal to modulus of dou r vector by dou x. Okay, so it is equals to 1. Therefore the unit vector ex, okay, so this is a unit vector ex. If we substitute these values in this equation, we have, instead of dou r by dou x, we can substitute as I cap, right? I cap divided by this hx is nothing but 1. Okay, so this is nothing but our I cap. This is our unit vector in the x direction. So what we done here is we derive this unit vector from for the Cartesian system using the generalized curvilinear system. Okay, so this is an example. So we can use this form to find other systems. So some of the other examples for curvilinear systems are spherical system, spherical coordinates, where the parameters u, v, w are u equal to r, v equal to theta, and w equal to phi. Okay, in spherical coordinates. So for cylindrical coordinates, this u equals to r, v equals to theta, and w equal to z. So before moving further, let's try to work out the unit vectors and the scaling factor for the spherical coordinates using curvilinear coordinates. Okay, so in spherical system we know that the axes are r, theta, and phi, right? So we can transform this r vector. So this is r vector in Cartesian. Okay, so r vector is x I cap plus y j cap plus z k cap. Okay, so this is in Cartesian. Okay, so we are trying to change this r vector in spherical coordinates, and we try to find the unit vector. So in the spherical coordinates, the unit vectors are not I, j, and k. So we have to find them explicitly. So for that we are using the curvilinear coordinate systems we worked out earlier to find these unit vectors of the spherical coordinates. Okay, so in order to convert this Cartesian to spherical coordinates, we have to transform this x as r sin theta cos phi, and y as r sin theta sin phi, and z as r cos theta, right? So if we substitute this, then the position vector in position vector of p, which is the r vector in the spherical coordinates, can be written as r sin theta cos phi I cap plus r sin theta sin phi j cap plus r cos theta k cap. So this is the position vector in spherical coordinates. Okay, in spherical coordinate system. So let's try to find the unit vectors for the spherical coordinates in using curvilinear systems. Okay, so in curvilinear system we know that from curvilinear system coordinates, we know that our dr is nothing but h1. So here our suffix are h of r, e of r cap, dr plus h of h theta, e theta cap, d theta plus h phi, e phi cap, d phi, right? Since our axes are r theta and phi. Okay, in spherical coordinates our axes are r theta and phi. Okay, and also we know that er cap equals to 1 by hr dou r vector divided by dou r, and e theta cap equals to 1 by h theta dou r divided by dou theta, and E phi cap equals to 1 by H phi dou r theta, dou r divided by dou phi, right? Okay. So what is dou r by dou r vector divided by dou r? Dou r vector divided by dou r is nothing but sin theta cos phi. I am writing this from this equation. Okay. So if we differentiate this r vector with respect to r, we have sin theta cos phi I cap plus sin theta sin phi j cap plus cos theta k cap, right? Okay. So next what we have to find? We have to find this HR. Okay. So this HR is nothing but modulus of dou r divided by dou r vector divided by dou r. So it is nothing but square root of dou r vector divided by dou r dot. So this is a dot product. Dot with dou r vector divided by dou r. Okay. So if we take the dot product, we have square root of sin square theta cos square phi. Since we are taking dot product with itself, so this I cap, and we also have, and this I and I becomes 1. Okay, if we take dot product, so we have sin square theta cos square phi plus sin square theta sin square phi, right, plus cos square theta, right? Okay. So we can take sin square theta here outside, so we have square root of sin square theta of cos square phi plus sin square phi plus cos square theta, right? So this reduces to root of sin square theta into 1 plus cos square theta. So this further reduces to root of 1, which is 1. Okay. So our HR vector, sorry, the scaling factor HR equals to 1. Okay. Similarly, we can find this this dou r vector by dou theta. Okay. So this dou r vector by dou theta. So we need this dou r vector by dou theta because we need to find the unit vector, this E theta cap, right? So for that we need dou r by dou theta. Similarly, we also need dou r by dou phi. Okay. So let's try to find first dou r by dou theta. So what is dou r by dou theta? So from this we can find the expression for r. So we have to differentiate it with respect to theta. So we have r cos theta cos phi. So we have r cos theta cos phi I cap plus r cos theta sin phi j cap. Right, let me check it again. So we are differentiating with respect to theta. So we are differentiating sin theta, right? Okay. So sorry, here it is not phi, it's theta. Okay, and we have this r cos theta, right? R cos theta. If we differentiate it with respect to phi, we have r, so it's minus r sin theta k cap, right? Okay. So let's try to find our h theta. Okay, h theta, the scaling factor. So this h theta is nothing but dou r divided by dou theta. Okay, this modulus. So it is root of dou r divided by dou theta dot with dou r divided by dou theta. So we will have r square cos square theta cos square phi plus r square cos square theta sin phi sin square phi plus r square sin square theta, right? So, and we also have a root here, so it is 1 by 2. Therefore we have r square. Let's try to take this r square cos square theta outside from this. So we have r square cos square theta is cos square phi plus sin square phi, right? Plus r square sin square theta whole power 1 by 2. So this one gets equals to 1, and we have r square cos square theta plus sin square theta, right? And we also have a root outside. Therefore this also equals to 1. Therefore we have root of r square, which is nothing but r. Therefore our h theta, the scaling factor, is r. Okay. Similarly, next we have to find dou r vector divided by dou phi, right? So dou r vector divided by dou phi is, we have r vector sin theta, so it's cos phi, so it's dou r by dou phi is minus, we have a minus sin phi, right? We have a minus sin phi here, plus r sin theta, we have a sin phi here, so if we differentiate we have cos phi, and there is no other, this is j cap. I left this unit vector, so let me try to add this unit vectors, and the coefficient of k cap is cos theta, and if we differentiate it with respect to phi, it's 0, right? Okay. So we have minus r sin theta sin phi I cap plus r sin theta cos phi j cap, right? So to proceed further, what we have to do next, we have to find this scaling factor h of phi. Okay, so this h of phi is nothing but the modulus of dou r vector divided by dou phi, so which is nothing but root of dou r vector divided by dou phi dotted with dou r vector divided by dou phi. So we have r square sin square theta sin square phi plus r square sin square theta cos square phi, right? So we also have a root outside. So from this we can take r square sin square theta as common. Therefore we have r square sin square theta of sin square phi plus cos square phi, and whole power 1 by 2, and this turns out to be equals to 1. So we have root of r square sin square theta, which is nothing but r sin theta. Therefore the final scaling factor h of phi is r sin theta, right? So let's rewrite the unit vectors. So we know the unit vectors E of r cap equals to 1 by h of r cap, h of r dou r divided by dou r vector divided by dou I, okay, which is equals to, so what is h of r? H of r is 1, and this dou r vector divided by dou r is, what is dou r vector divided by dou r? The dou r vector divided by dou r equals to this one, okay. So let me copy this and paste it here. So this is our new unit vector in spherical coordinates, and this is the unit vector along the radial direction, r direction, okay. Next we can write this E of theta, okay. E of theta equals to 1 by h of theta dou r vector divided by dou theta equals to, so what is h of theta? H of theta is r, okay. So we have 1 by r, and this dr vector by d theta equals to this one, okay. So what we have to do, we have to, okay, let me copy it from here and paste it there. So dou r vector divided by dou theta equals to, sorry, this is not dou r by dou theta, it's dou r by dou phi. So we have to find dou r by dou theta. So here we have dou r by dou theta. So if we divide by r throughout this equation, we have E theta, the unit vector along the theta direction, as cos theta cos phi I cap plus cos theta sin phi j cap minus sin theta k cap, right? So this is the unit vector along the theta direction. So finally we have to find the unit vector e phi of e phi cap equals to along the phi direction as 1 by h of phi into dou r vector. So this is dou r vector divided by dou phi. Okay. So what is h of phi? H of phi is r sin theta, right? So it is r sin theta into dou r by dou phi. Okay, let me copy dou r by dou phi. So this is our dou r by dou phi. So if we divide this equation by r sin theta, we have sin phi I cap, and we have minus here, plus cos phi j cap. Okay, so this is our e of phi, the unit vector along the phi direction. Okay, so this is the unit vectors and the scaling factors. So this is for spherical coordinates, and we found this using our general curvilinear system. Okay, so let me move on to the our main aim. So our main aim is to find the vector operators in what's called in the generalized curvilinear system. Okay, so what are the vector operators? So the vector operators are the gradient operator, divergence operator, curl operator, and Laplacian. Okay, so let's try to work out the form of this del, right? So this is our vector differential operator using curvilinear, okay, generalized curvilinear coordinate system. So our aim is to find this del vector, so that we can convert this gradient or the divergence or the curl for this new the generalized curvilinear system. Okay, so for that let's have a let's try to find the gradient for a scalar function phi. So our aim is to find the gradient of a scalar function phi in curvilinear system. Okay, in curvilinear system we are going to find the gradient, okay, the form of gradient of a scalar function phi. Okay, so in curvilinear system we know that phi must be a function of u, v, and w, right? Since we are in a curvilinear system, so let's try to find d phi. Okay, so d phi is nothing but dou phi by, since it's a function of u, v, and w, we have to find the partial derivatives. Dou phi by dou u into du plus dou phi by dou v into dv plus dou phi by dou w into dw. Okay, so since our aim is to find the gradient, let's try to use the orthogonality property. So we know that in Cartesian system, in Cartesian system, we know that I cap dotted with I cap equals to 1, right? Similarly, j cap dotted with j cap equals to 1, and k cap dotted with k cap equals to 1. Similarly, in orthogonal curvilinear system, this e u cap, since this e u cap is a unit vector in curvilinear system, so this e u cap dotted with e u cap equals to 1. Okay, and this e v cap dotted with e v cap equals to 1, and this e w cap dotted with e w cap equals to 1. Okay, so this is in Cartesian, and this one is in curvilinear. Okay, so this is the orthogonality property. So we can exploit this orthogonality property to find the gradient. Okay, so let me use this EU here, okay, in this equation. So this d phi now can be written as dou phi by dou u in du into eu cap plus dou phi by dou v dv ev cap, okay, and this dou phi by dou w dw into e w cap, okay, and not this eu here. Okay, let me rewrite this again. Okay, so let's write this d phi as dou phi by dou u eu cap plus dou phi by dou v ev cap plus dou phi by dou w ew cap dotted with du into eu cap plus dv into ev cap plus dw into ew cap. Okay, so if we make a dot product and if we use this orthogonality property, this form reduces to this one. Okay, so both these expressions are same. Okay, so the motivation is to find, so to convert this side, this du dv and dw to dr. Okay, something like dr. Okay, so this is our motivation. Then we can rewrite this one as a gradient. Okay, and this gradient is a gradient of the function phi in curvilinear system. Okay, so we also know that dr vector equals to, what is our dr vector? It's hu eu cap du plus hv ev cap, sorry, it's ev, right, ev cap dv plus hw ew cap dw. Okay, so this is our dr. We already worked out this one. So our motivation is to convert this equation to this one. Okay, so that we can write this as a as dr. Okay, in this part. So for that let's multiply this whole equation by multiply and divide this whole equation by hu, hv and hw. Okay, let me write it out. So it's 1 by h1, sorry, hu. Here what I am doing is I am h and hu. Okay, so this is 1, and this dou phi by dou u eu cap plus hv by hv, sorry, this is hv, dou phi by dou v ev cap plus hw by hw, dou phi by dou w ew cap. Okay, dotted with this du eu cap plus dv ev cap plus dw ew cap. Okay, so next I am moving this numerators, right, this numerators to this side. Okay, it's not the other side, so I am just relocating this hu, hv and hw to this equation, so that I can rewrite this equation as dr. Okay, so that's the motivation. So if we relocate this hu, hv and hw, we have 1 by hu d phi by, sorry, dou phi by dou u into eu cap plus 1 by hv dou phi by dou v ev cap plus 1 by hw dou phi by dou w ew cap dot, so always remember it's a dot product, dot this one. Okay, dot with h1 eu cap du, okay, plus sorry, it's hu. Okay, so hv ev cap dv plus hw ew cap dw. Okay, so if we multiply this, we have this equation. Okay, and this is similar to this one, and this equation is similar to this one. Okay, so what we did is we just use the orthogonality property, and we try to rewrite this d phi as something like a gradient dotted with a dr. Okay, so from this equation is nothing but our dr. Okay, so this is our dr, so we can substitute. So our d phi equals to 1 by hu dou phi by dou u eu cap. Okay, instead of putting this phi here, let me write it in a common, take it out as common factor, plus 1 by hv dou by dou v of ev cap plus 1 by hw dou phi by dou w ew cap of phi dotted with, and this one is nothing but our dr vector in curvilinear system. Okay, and from this equation, it's a familiar one in the Cartesian system. In Cartesian system, this d phi equals to gradient of phi dotted with dr. Okay, so here also it is similar. So this part is nothing but our gradient in curvilinear system, right? Therefore our del operator, so the vector differential operator, this del vector in curvilinear system turns out to be equals to, our del operator in curvilinear system is nothing but 1 by hu eu divided by hu dou by dou u plus ev cap by hv dou by dou v plus this is e. Okay, so this is ew cap divided by hw into dou by dou w, right? So this is our new vector operator. In curvilinear system. Okay, so this is our del operator in curvilinear system. Similarly, we can find the divergence. Okay, divergence in curvilinear system. Okay, so so in order to find the divergence, let's suppose we have a vector function. Let's f vector be a vector function in curvilinear system. Therefore our f vector is a function of u, v and w, right? And this f vector is given as f1 eu cap plus f2 ev cap plus f3 ew cap. Okay, so these are the unit vectors. And this f1, f2 and f3 are the coefficients. Okay, let's use this formula for del to find the divergence in spherical coordinates. Okay, so for spherical coordinates, so what are the spherical coordinate axes? R, theta and phi. Okay, so these are the parameters, and we know that h1 equals to, our hr equals to 1, and this h theta equals to r, and h phi equals to r sine theta. Alright, let's check one more time. So what is our it's so h of phi is r sine theta, and h theta is r, and hr equals to 1. Okay, so let's substitute this, and the gradient of any scalar function, gradient of phi, okay, in r, theta and phi. Okay, so So here we have a confusion. This phi is the angle. Okay, so let me rewrite this into another form. So gradient of some scalar function f. Okay, some scalar function f, which is a function of r, theta and phi, can be given as del. Instead of del, what we have to write? We have to write er cap. Okay, er cap, and our hr is 1 dou f by dou r plus e theta cap divided by r dou f by dou theta plus e phi cap divided by r sin theta. This is because of our h phi. Okay, so here we have h of w. H of w is nothing but h of, so what we are doing, we are mapping this u, v and this v. Okay, u, v and w to r, theta and phi. Okay, so that's why we have to substitute r instead of u and theta instead of v and phi instead of w. Okay, in this equation, and we have dou f divided by dou phi. Okay, so this is our gradient. Okay, gradient in spherical coordinates. It's an example of using curvilinear, using gradient found using the curvilinear, generalized curvilinear coordinates, and we apply the parameters u, v and w for the spherical coordinates. Okay, and this is the expression for gradient. And this er and e theta and e phi are the unit vectors along r, theta and phi, and it is given in this, it is worked out earlier. Here it is already worked out. Okay, so next let's try to find the divergence of a vector field using curvilinear system. Okay, so let f be a vector field in coordinate in curvilinear system. Okay, curvilinear system. Therefore our f vector is a function of u, v and w, right? And we can write f vector as f1. so this is the coefficient of the f vector along eu direction, right? Similarly we have f2 of ev cap and f3 of ew cap. Okay, so this is similar to our Cartesian system. In Cartesian system, this f is a function of x, y and z, and we represent it as f1 of I cap plus f2 of j cap plus f3 of k cap, right? So this is in Cartesian, and this one is in curvilinear. Okay, so this is in curvilinear system. So let's find the divergence. So we know the expression for divergence is del dot f vector. Okay, and we know our del is nothing but eu cap by hu dou by dou u plus ev cap by hv dou by dou v plus ew cap by hw dou by dou w. Okay, so this is our del in curvilinear system, and we have to make a dot product with our f vector in curvilinear system. Okay, so this is our f vector. So f1 of eu cap plus f2 of ev cap plus f3 of ew cap. Okay, so since these unit vectors also obey orthogonality, we have this eu cap dotted with eu cap equals to 1, and similarly it is for all the indexes. Okay, so ew cap dot ew also equals to 1. Okay, therefore what we have is, so if we make a dot product, we have 1 by hu into dou f1 divided by dou u plus 1 by hv dou f2 by dou v plus 1 by hw dou f3 by dou w, right? So this is our divergence. So further we can simplify this by taking this hu, hv, hw is common, and we can write 1 by hu, hv and hw into dou f1 divided by dou u into hv, hw plus dou f2 divided by dou v into hu hw plus dou f3 divided by dou w into hu h. Okay, so this is our divergence of an f vector in a curvilinear system. Curvilinear coordinates. So let's work out an example for this. So let's find the divergence of a vector f vector in spherical coordinates. Okay, so in spherical coordinates, so this is an example. Okay, so in example, so we are using spherical coordinates. So in spherical coordinates, we know h of r equals to 1, and h of theta equals to r, and h of phi equals to r sine theta, right? So this is our spherical coordinate, and our u, v and u equals to r, v equals to theta, and w equals to phi. Okay, so let's work out this for, first we work out for the gradient. So what's the expression for gradient? We have, so we have er cap and let's try to find out divergence of this f vector in spherical coordinates using this generalized curvilinear coordinate formula. Okay, so for spherical coordinates, we have hr equal to 1, h theta equal to r, and h phi equals to r sine theta. Okay, so if we substitute this here, we have our this divergence of f vector equals to hu. So for u, we have to substitute hr, h theta, and h phi. Okay, dot dou f1 vector by dou r h theta h phi, right, plus dou f2 divided by dou theta hr h phi plus dou f3 divided by dou phi hr h theta, right? Okay, so if we substitute these values of hr, h theta, and h phi in this expression, we have 1 by r square sine theta, okay, r square sine theta of dou f1 divided by dou r into this h theta and h phi is r square sine theta plus dou f2 by dou theta, and this hr is 1 and h phi is r sine theta, so it is r sine theta, plus dou f3 by dou phi, and hr is 1 and h theta is r, so we have a r here. Okay, so let's try to simplify this further. So we have dou f1 divided by dou r. Okay, since this r is inside this derivative, we cannot take this r outside, so we have 1 by r square sine theta into dou f1 divided by dou r square sine theta, right? Since this derivative is with respect to r, we cannot take this r outside, we can take sine theta only. So this sine theta and this sine theta get cancelled, and we cannot use this r square, we cannot strike out this r square because the derivative is with respect to r. Okay, and this one we have dou f2 by dou theta, and since the derivative is with respect to theta, we cannot strike this 1 by r square sine theta dou f2 divided by dou theta r sine theta. Since the derivative is with respect to theta, we cannot strike this theta and this theta, so we can only simplify this r and this one. Similarly for this 1 by r sine theta, r square sine theta, dou f3 divided by dou phi of r. Okay, since there is no phi terms here, we can simplify this one. So finally we have 1 by r square dou f1 divided by dou r into r square plus 1 by r dou f2 by dou theta sin theta plus 1 by r sin theta dou f3 by dou phi. Okay, so this is the expression for divergence of f vector in spherical polar coordinates, spherical coordinates, and we derived it using our generalized curvilinear coordinate system. Okay, similarly the curl of f vector in curvilinear system can be written as curl of f vector is nothing but del cross f, and is equal to 1 over hu hv hw of determinant hu eu cap is hv ev cap hw ew cap. We have the derivatives dou by dou u, dou by dou v, dou by dou w, and the coefficients hu a1 f1, okay, f1 hv f2 hw f3. Okay, so this is the expression for the curl of f vector in curvilinear system. Okay, so with this we have finished the last part of the vector calculus in our syllabus, and it's about vector operators in curvilinear system. So these are and we have also included some examples of using this curvilinear system to find the vector operators of spherical coordinates. Okay, so with this vector calculus part is over. So next we can work out on the linear algebra. It's about the determinants, finding eigenvalue, eigenvectors, and the diagonalization of matrices. Okay, so I will talk about those things in the next video. Okay.